Hello. In this screencast, I wanted to show you an example problem that I'm going to work out two different ways. In this first video, I'm going to show you how to work out number 6 using a geometric approach. Okay? And then the next video, I'll show you how to work out problem 6 using more of an algebraic approach. It says, in the motionless system below, the ramp and pulley are frictionless. Okay? What is the mass of block B? It's like block B is hanging by a frictionless pulley, and there's a rope wrapped around there attached to a 200 Newton weight, and the ramp's frictionless, the pulley is frictionless, and that means the block can slide freely on the ramp. And let's see, what else? We want to find the mass of the block, and we want to see if the answer changes if the angle is increased to 70 degrees. Interesting. So first thing you want to do is try to make sense of this and say, well, due to this word here, the word motionless, that implies that my change in velocity is 0. Or in other words, my acceleration is 0. Therefore, thus, since that's true, then I can say that the sum of the forces acting on both the 200 Newton mass and the hanging mass, the sum of the forces has to be 0. And I'm going to treat the two objects as separate systems. Okay? So let's start with a hanging mass, mass B. Okay? So this is true for both systems. Now again, this is only one way of doing the problem. You could do it a lot of different ways. But my approach, I'm just going to kind of divide and conquer here. And first I'll start with system B. That's the hanging mass. Okay? And let's see here. There it is right there. So I'll make that my system. And if we have an equilibrium situation, then the tension in the rope and the weight have to add to 0. Okay? So T up, weight on object B pulling down, so tension is due to rope. These have to add to 0. So let's see how that might work. T, let's see here. I'll fix that. There we go. Here's a little bit behind me. Let's give it a second. All right, now the eraser should show up. And let's try that again. T rope, which is that force. Okay. Plus weight down. So these two vectors actually must add to 0, like that. So in other words, T is the same magnitude as the weight of object B. Okay? That's what that force diagram is telling me. Let's see what we can figure out from our 200 Newton system. So this is the system that's sitting on the ramp. Okay? So block on ramp system. Okay? And I'm going to draw this over here. Just so I can get my forces in the correct direction, I'm going to use my diagram. Okay? So I'm going to have a normal force that's at an angle, kind of like that. Let me fix this. Okay? So my normal force is going to be like that, perpendicular to my surface. That'll be my normal. Force due to surface, normal due to surf. I just like saying the word surf. Weight is going straight down because that's the force due to the earth pulling. Okay. And what else do we have here? We don't have friction because it says the surface is frictionless and the pulley is frictionless. We have a rope that's pulling that way. Let me fix that direction. That's not very good. There we go. Oh, that one's not so good either. Let's do it. There, that's pretty good. So this will be my tension due to rope. Okay? And this tension going at an angle to the right must be in the same as the same magnitude, the same amount of force as this tension here and this tension. These have to be in the same magnitude, same strength. Okay? So if I can figure out that tension, I can figure out the weight because they're equal to each other. The weight of object B, that is. And this weight going down, I know. So I'm just going to call this W. And I'm going to label it 200 newtons because I know that it's 200 newtons. Okay? And let's see here. I have some angles to deal with here. Okay? So I might as well label my angles right now. So I'm going to draw a horizontal reference line. Oh, that's not such a good reference line. Try again. There it goes. There's a reference line. Maybe I'll draw a vertical reference line going up. Okay? So the angle that my ramp is tilted, this angle should be this angle here. Okay? I don't have much room there. So I'll label it here, 35 degrees. And that's the same, the ramp is tilted the same amount that the normal force has to be tilted from the vertical. So this one is also going to be 35 degrees. And what's 90 minus 35? Okay, let's figure that out. That should be what? 55 degrees. All right, so that means this angle is 55 degrees. And this angle is 55 degrees. Okay, cool bananas. Let's carry on. All right, so the forces on the block that's on the ramp, those forces need to add to 0. So let's see how that works. See here, this one is probably going to be a bit longer, maybe like that, I'm guessing. Okay, I'll put this down here. Okay, that'd be nice. And let's see here. Okay, I'm going to move this down just a little more, give myself some room, and I'll add my tension next. I just like adding my weight in last because I know my weight is straight down. So I just adjust the lengths of my arrows. And it looks like this one should be a little bit longer. So I'll just stretch it out a little bit. Too bad it's not straight. I better fix that. Okay. Okay, let's see if I can do a nice job here. It would be helpful to use a ruler. So this is my normal force. This is my rope. Is that right? Yeah, this is the block on the ramp. Right. And this force going down, straight down. That should be my weight. Right? It's pretty good. And let's go back up to our diagram. I'm going to need a little bit more here. If I continue this down like that, I continue this one like this, I should be able to figure out that, let's see, these angles should alternate, right? This one will be 35 degrees. This one will be 55 degrees. This one will be 35. This is a pretty common pattern. And this one will be 55. I'm not saying it always happens this way, but quite often I do remember the angles alternating like this. All right. So let's figure this out. The normal force looks like it's making a 35-degree angle with the vertical. So that means this angle here is 35 degrees. And yeah, we're probably going to have to use law of sines here. I don't see this. Well, wait a second here. This might be a right triangle. Normal force and tension are a right triangle because normal force is perpendicular to the surface. Tension is parallel to the surface. So this is going to be a right triangle. Cool, dude. Well, okay. So what's 100? Let's see, 90 and 35. That's going to be 125. So it's 180 degrees minus 125 degrees. Let's see what we got here. 5, 7. Let's see here. This is 5. Is that a 55-degree angle? Whoa, that actually makes sense because the down, let's see, this force, this angle here is the tension, the direction of my tension makes with the vertical, okay? So yeah, that's got to be 55 degrees. The rest of this problem is going to come down to strategy here, because if I can find the tension, if I find the length of that side, I should be able to find the weight, and it looks like for part A, what are we trying to find? We're trying to find the mass of object B. Well, I could easily find the weight of B. I mean, once I find the weight of object B by finding the tension, I can convert that to mass, and I'm good to go. Okay, so I really only need my tension. So sine 35 degrees, oops, that was nice, haha, sine 35 degrees over, what is it, t, which is what I need, I'm trying to find that, should be equal to sine, oh, why am I using law of sines? Duh, I can use cosine or sine. I know the weight is 200 newtons. What was I thinking? So 200 newtons here. Yeah. So we know our hypotenuse is 200 newtons. We're looking for t, so let's use sine 35 degrees. I think that'll be pretty easy. Sine 35 degrees is going to equal opposite, which is tension, over 200 newtons. So tension is going to equal 200 newtons sine 35 degrees. Done deal. I can put that in a calculator. Clear it. Sine 35 degrees equals some decimal times 200. That's going to be 115 roughly. So my tension, make sure my calculator's in degree mode. But that number makes sense. 115 degrees. Sorry, 115 newtons. This is the force of tension in the rope. Okay? There we go. Now, the weight of object B is also equal to 115 newtons due to first law. Right there. So now that I know the weight of object B, let's just work out the mass. Weight of object B is equal to 10 newtons per kilogram times the mass of object B. The mass of object B, therefore, is going to be the weight of object B divided by 10 newtons per kilogram. So that's going to be the weight of object B, which is 115 newtons, divided by 10. Newtons are going to cancel. And I got 1 over kilograms, so that gives me kilograms in the end. So what's this? 11.5? So I'm talking about 12 kilograms, roughly. And part A is now done. This is the mass of block. No, it's the hanging mass. Cool, man. Let's see what part B is all about. Part B says, how does this answer change if the angle is increased to 70 degrees? Oh my gosh. Okay. So if the ramp gets steeper and steeper, oh my goodness, what's going to happen? Well, this force diagram is going to change. Here, why don't we just do this? I'll work it out right over here. Instead of saying sine 35 degrees, it would be sine 70 degrees is equal to T over 200 newtons. So T is going to be 200 newtons sine 70 degrees. All right, let's see what that is. Sine 70 degrees. I'm predicting a big rotation here. Times 200. I don't know what gave me that idea. So now we're talking about 188 newtons for the tension in the row. Hopefully it doesn't break. And the only way this could happen is if we had a larger weight. So if the tension is 188 newtons, the weight of object B would have to be 188 newtons. That's the hanging mass. Or it just wouldn't work. The block would slide down the ramp. Now, with what motion would it slide down the ramp? All right, and the mass of object B is going to be about 19 kilograms. That's the mass you would need to keep the system in equilibrium. So, all right, required mass to keep equilibrium. Equilibrium means the sum of the forces is equal to 0 still. So if you want to keep equilibrium at an angle of 70 degrees. Pretty cool. And that's how you do problem 6 using a geometric approach. Thank you for watching. Have a good night.